Now we're going to move to the third session. It's about technology against COVID-19, where we're going to see how technology and new technology can help in combating COVID-19. The floor is given to Associate Professor Mahmoud al-Misallawi, Faculty of Engineering, Helwan University, one of the moderators of this session. Now, تفضل Professor Mahmoud.
Good evening, everyone. Welcome for all of you in the third session of the International Virtual Conference in COVID-19, organized by the Hub for Creativity and Scientific Research in Helwan University. First of all, I would like to thank all of you for joining us in this conference and especially your interest in this session. My name is Mahmoud al-Misallawi, an Associate Professor of Electronics and Communications in the Faculty of Engineering at Helwan University. And I am blessed to be one of the moderators of this session number 3, that talks about technology against COVID-19 pandemic. It is also an honor for me to introduce my colleagues who will participate with me in coordinating this session. Dr. Ruwaida Sadiq, an Associate Professor in the Faculty of Computer and Artificial Intelligence, and the Director of the Research Hub at Helwan University. And also my colleague, Dr. Ahmed Aisawi. He is an Assistant Professor of Biochemistry and Molecular Biology and the Director of Bioinformatics Center in the Faculty of Science at Helwan University. Actually, technology is one of the main arms that many countries around the world have relied on to provide some innovative and applied solutions that can help to limit and control the spread of this new type of coronavirus. For this, we will discuss in this session the potential of different technologies against COVID-19 pandemic. And also we will show for you some of the research contributions and the research projects conducted at Helwan University, actually that rely on the use of technology to combat and control the coronavirus or COVID-19. According to our agenda of this session, we have mainly 4 talks. Let me, due to the time, introduce the first one, which is a really very interesting talk. Actually, as the other talk are also very interesting. Actually, the first talk talking about technology innovation possibilities for COVID-19 that will be presented by Dr. Mohamed El-Dakroury. Dr. Mohamed El-Dakroury is an Assistant Professor of Microelectronics in Electronics and Communication Engineering at the Faculty of Engineering at Helwan University. And he is also a researcher at the Center of Nano-Electronics and Devices in American University in Cairo, and the Deputy Manager of Innovation and the Product Development Support Center at Helwan University. Also, Dr. Mohamed have more than 15 years of experience work in different technologies and mainly related to the information and the communication technology, as he was a former R&D manager and engineer in many companies in Egypt and actually in the United States of America. And today he will be sharing with us his expert opinion in the technology domain and how it can be used in the fight against COVID-19. With that, I ask all of you to give your full attention to Dr. Mohamed and enjoy his talk. And now I will give the floor to Dr. Mohamed to start his presentation. Please, Dr. Mohamed, go ahead.
Thank you, Dr. Mahmoud. I thank Dr. Majid Negm and Dr. Mona Fuad and Dr. Ruwaida Sadiq and the panel for organizing such a wonderful conference with multidiscipline. Actually, it was very enriched, having, many topics, especially in this, bad situation that the whole world is going through now. Thank you for that. I will start my talk by saying that since the situation of this pandemic is not easy, the human being now, they are trying to use all the tools they could use. Even there are such technologies that were not used before in such emergency situations. Now they are trying to use all weapons they can use And actually, I give a big applause to China because they have employed a lot of technologists. Maybe you have used all of them in a very short time. That means that they were very well prepared for that pandemic. This talk is not meant to dig deep in each technology, but have a glimpse and a fast touch, so we will be aware of them, or most of them. So this may open the door, you know, to think and ponder about research tracks that might be interesting for Helwan University researchers. Also, this will encourage, you know, multidisciplines to cooperate together, since those technologies are tackling, you know, multidiscipline fields. I will start sharing now my screen. Okay, what's the motivation? The motivation is the general motivation, of course, is to mitigate the spread of the virus, to minimize again till developing a vaccine. So this is the general motivation. And of course, all of us saw this curve before many times, many times, which is we want to flatten the curve. So flatten the curve, so we take the burden of the exhausted, you know, healthcare staff, and in the same time try to minimize, you know, the infected people at a time and the number of deaths. What about technology? Let us go more narrower. We need to focus about technology role in fighting this pandemic. So first of all, the most important thing, it is the need of information. Need of information doesn't only come with this situation only. Now we are in the information age, as all of you know. This means that the information now is the most precious thing. So need information here is fundamental in fighting this pandemic. Why do we need information? We need information to have a better control on the situation. And there is some requirements for the prevention control, and there is a full requirement. If any one of you can go to the WHO website and check for this. So these measures is being done to have a better control. Also to treat patients effectively. So needs of information also needed to treat patients effectively. So there are some applications like telehealth, for example. We'll talk about it in a little bit of detail later. Also, why do we need information? To finally, or maybe one of the goals, minimize pressure on the exhausted health staff. So this is maybe a focused sub-goals related to technology. Okay, so who needs information? And why do we need information? Do we need information for better decision making? So who will do the decision making? Who needs information? 4 categories. First one, epidemic disease modelers. They are the ones, the models, you know, or provide finally the mathematical curves that track, you know, the spread of the virus. All of us, of course, went to these websites and they checked those curves before. Who needs them else? The authorities, all kinds of authorities, the top authorities, the health authorities, local health authorities, I mean, in each state, on each country. Also the WHO, which means international organizations. Also the people, the regular people. Why do we need regular people needs information? Because if they know if there is a suspect case around, they will take care, and if they will take care, this will help, you know, fight the pandemic or decrease its increase. So here are some technologies very famous now, or it was applied maybe partially or fully, depending on the situation in each country, depending on the type of technology. We will go through very fast in the slides. First, Internet of Things, blockchain, telehealth, or what's called telemedicine. Maybe telemedicine is a part of the telehealth. 3D printing, nanotechnology, synthetic biology, and there are other things called gene editing. robots and drones. Some people put drones in a separate bullet, but I consider, robots and drones doing, a job very similar to each other. But the issue is, it's not the technical issue of applying such technologies. Technologies will have, for example, not everybody will like to adopt such technologies. That's why there's another dimension, which is the socio-ethical issue. The socio-ethical issues related to the security and privacy. And this will lead to the public trust in using such technologies. Because you cannot, maybe it can in some countries, but you cannot enforce these technologies on the people's lives unless they are they are comfortable using it. But of course, it can be enforced in other domains within certain organizations. So this is the social or the socio-ethical impact is another dimension, very important, that many times limits the use of such technology. So the technology could be advanced and could do some good impact, but unfortunately, we cannot use it effectively because of this resistance coming from the society. We will start first. The first technology is artificial intelligence, and it's very important to do tracking and prediction. Actually, there is a startup company in Canada called the Blue Dot. They expected by their AI engines using what's called NLP, natural language processing, which is a form of analysis being done to texts or images of texts, like optical character recognition, like a speech recognition, and such stuff. So NLP, in conjunction with what's called machine learning, which is a part of the AI, this company used such engines to scan news reports and airline ticketing data. And they could, extract some information that alerted that there is a pandemic is going on and is going to continue. And this alert was at December 31st. Do you know when WHO announced there is a pandemic called COVID-19? It was on January 30. On January 30. Also, another example, there are like 3 or 4 examples of early prediction of pandemic, but this is another second example, which is Boston Children's Hospital has their automated health map system, also could generate on December 30 an alert also based on online news and social media reports. So as you can see, this is one direct application of AI, is prediction, trying to predict what could happen. But of course, there is a price paid. This information might not be accurate, or there is a certain accuracy, or maybe some people, as are going to come and see later in the second slide. We'll talk about this later. But I will talk about this company called the Blue Dot, which is a Canadian startup. They used, of course, before I explain this, I will give you a first glimpse of how AI works. AI, it has a part of it called machine learning, and it means that the machine or the computer try to mimic the human thinking, human brain. That's why it's called artificial intelligence. So the scientists studied, the brain. They found it consists of what's called neurons, and these neurons, a lot of neurons connected in a very complicated network together, and based on training them or historical data, a processing will happen in this network, and then an outcome will come. Of course, when they started with this AI or machine learning, this machine learning depends, its intelligence depends mainly on the training it. We have to train it well training it. How to well train it? By feeding it with good history, good representing history. So it will be good trained, and if it's good trained, it can, if it has a different input, it has enough experience to come up with an output that is, with good accuracy. So this Blue Dot company, it has top scientists. If you can go to their website and check, they published a paper on the International Society of Travel Medicine, and they used a 40 pathogen specific data sets. Pathogen means virus or any agent that will cause disease. So they take what's called data set. Data sets is like a representing good input for the AI network in order to come up with a good output and give us good prediction. So they use a 40 pathogen specific data sets to previous diseases very close to the coronavirus from the mobility and outbreak potential point of views. And they feed this to the network. And then they come up with they took look at the data coming from the airlines, from different airports. And as you see, there is a table here. Here's a table here. Shows some numbers. And they come up with an index called IDVI, which this number varies from 0 to 1. If it is close to 1, this means that this country is more immune for the virus to go through it. But if it goes below, closer to 0, this means that there is a potential of the pandemic to spread in this country. That's why they could, by calculating such index, and this index depends, if you go to the paper, depends on 7 parameters. I will mention maybe 2 or 3 of them. One of them is the demographic, the health care, the public health, the economy, the political situation, and many 7 items. They could, calculate with a certain formula this index, and then they could, anticipate or expect where the virus will spread next, which countries, and for some, it has some good accuracy. Maybe if we take another example, we'll show here because it was not shown in this paper actually. But another company called Metabuta, and by the way, there is what's called MIT Technology Review. They have done a very good review at this point. This company Metabuta, they predicted on February 25 that on March 3 there will be an accumulative 127,000 cases worldwide. And this was an overshoot error by 30,000. Some people say it's a big number, big error, but actually, one of their top managers see it's okay. At least, it give you a good indication of what's going on. And also, it successfully predicted the countries of potential spread at that time: China, Italy, Iran, and USA. So actually, it was pretty much successful. But this provides trends, and sometimes the accuracy of data is not acceptable. So you cannot rely on this. They will tell you they could overestimate or underestimate things according to the situation of calculation. So what could be the killer thing? The killer thing is if you don't have enough data to feed it to the engine, then this will cause inaccuracy. And actually, the most important problem with information is its lack of data. Lack of data causes a lot of problems, and this will limit the use of AI and will not function effectively because of this. So lack of data is very important to take care of. Okay, so now we are talking about the first point with the prediction. This is a prediction, and this is an example of prediction. And we know what's the limitation of prediction now. So the second point is diagnosis. This is the one famous point of AI, and it succeeded very good, is that when they have the CT scan of a patient, by studying, CT scan, they can know, determine if this, without human intervention, if this patient has a coronavirus or not. So this will help, humans, which is a health staff, for diagnostic, especially with, the big number of patients around. But unfortunately, this cannot be used for early diagnostic, because for early diagnostic, the symptoms is not there on the patients yet. So it will not be shown on the CT scan of the lungs. So it cannot do early diagnosis. But at least, in the operation, while, detecting coronavirus for the patients that has already infected with coronavirus, it will help. It will help also to save time, because it has a good response. Third thing is treatment. Treatment, now when they are in the labs, medical staff, they are trying, many many paths. And unfortunately, also the virus has what's called mutation. Mutation, the virus, it changed itself. So now, after tomorrow is a different thing, you know. So the AI engine could, you know, simulate many paths and expect, you know, what's called all the situations of mutations. But unfortunately, this is the main issue. Is that also another thing? The lack of information. Again, the killer thing is that until now they don't have enough information, the scientists, about how the virus mutates. So we don't know what is the real situation will happen, because also there is lack of information again. So actually, the most successful point for AI is the diagnosis at this point, and they are working, you know, to enhance the treatment and prediction points. In summary, AI can be used for prediction, diagnosis, and treatment. Yes. Also, there's another point I didn't mention here, that it could dig and mine, you know, for big, you know, literature. We have a lot of papers, thousands of papers published. How the scientists will grasp all this information unless it has a good engine that can help him filter out, you know, such, you know, a very narrow point he is looking at. So using NLP, which is also, again, natural language processing, dealing with a lot of texts, huge amount of texts, it could, you know, handle such, you know, research. And there is an engine called the COVID Scholar Engine. This is the next slide, as you can see, from the University of California, Berkeley, one of the national labs was related to the federal government in the USA. And they have done a great job on such matter. So in conclusion, AI is an exciting possibility, but it's a far off one. It's not ready yet. And it couldn't, you know, have a good contribution now, because we are not still ready to have its full potential applied now. So this lack of information, so the main problem is the lack of information. It challenges the application of AI because of the numbers, which is the data means, and also another example, the virus mutation, which is, you know, the scientists now till now didn't, you know, have enough information or complete information about it. So this is about the AI. Let us move next. Of course, this matter could take, you know, hours and hours to cover, but as I told you in the beginning, we are going to have a fast touch on many technologies. AI doesn't work alone because it has to rely on data. So I try to increase the data. So the data could come from sensors, from devices, from many sources. So there is another technology, and I consider them very important technology nowadays, if it is employed with the AI. Internet of Things is that things talk to each other, which is non-humans. Devices, I will give you an example. For example, you know, a very, very famous example. The fridge we have in the kitchen, our kitchen, it is already smart fridge. It's programmed with a minimum and maximum quantity of, for example, tomatoes. If the tomatoes, you know, quantity is less than a certain quantity, automatically the fridge will sense that and will send, you know, a signal to the store, and the store will come. The representative will come, knock your door, and give you the tomato, and you don't have to pay sometimes also, because it's already deducting the money from credit card. So the things, you know, they are talking to each other for the comfort and the ease, you know, of human being life. This is an example. So this also can be used with coronavirus pandemic by employing what's called wearable devices. And this is a famous thing, because now if we impose these wearable devices on people, then they can sense temperature, because temperature now is an important symptom, you know, for the coronavirus. But unfortunately also, if the people does not want to adopt such technology, and you don't have a mean to impose it, so of course they will not wear this wrist or with this wearable device. So you lost some people, that you lost some information. So if you feed this to the AI engine again, it will not be enough information, so the outcome will not be accurate. And you will not be able to identify where is the infection is going now, or how to create an infection map, for example, accurate infection map, and to take measures for localized places, for example. So I will go, also there is another example, it's not mentioned here, for IoT. There are some applications that can use mobile devices. So you can be used to track, you know, the human being. For example, you get the information that this human being has a high temperature, but now I don't want to know where did he go, how many people did he meet, and where, and when. So using the mobile phone device with certain mobile application, there is a tracking can be happened, and some AI engine could be installed in these mobile devices and to process such data and come up with a good information for the decision maker. One of these applications is an application called Masari, was used at Faculty of Engineering at Helwan with Dr. Mahmoud al-Masalawi and his team. And also there's other, you know, applications, you know, used in Saudi Arabia and Emirates and other places in the world, have some similar ideas. And actually it was successful and to some extent also, and it helped somehow. Okay, next technology is the blockchain. Blockchain, of course, some of you maybe blockchain, maybe we didn't hear much about it because it's a, maybe could be a technical word. Maybe people heard about the cryptocurrency, Bitcoin, and such stuff, and what's called mining. People mine, you know, to get some coins, and the Bitcoin price is raised from whatever, how much dollar to very thousands of dollars. Of course, you heard about this. So the basic thing is the blockchain. This is the backbone of the cryptocurrencies. It is a database based on collaboration between participants with no central location nor central management. So this decentralization make it trustable more, because everybody in the network, in the blockchain network, has to agree. If a transaction happens, everybody has to agree and approve such a transaction, verified and validated. So this means that, you know, it's very hard, you know, that all people agree on something wrong, or, you know, doesn't, you know, violates the reality, or because all of them has an interest, you know, that everything will go correctly. Otherwise, he will be affected, this person. So actually, decentralization of the blockchain make it trustable source and make it, you know, a good technology to rely on. And actually, it's a cheap technology. It's a cheap technology. It doesn't cost much. Of course, people might, you know, disagree on this point because there are many types of blockchain networks. There are permissible one and non-permissible ones. And of course, the non-permissible one is the most trusted one because it's open to everybody. But in healthcare, it is better to use the permissible one because there is what's called an electronic health record. And EHR, the electronic health record, we'll go here. I don't know, maybe this one, yes. This is, you know, blocks showing, you know, this is, it's called blockchain. It's chain means the chain. The blocks connected after each other in a cascaded or a chain shape. And there's a cryptographic, you know, hash means that the transaction between the blocks are encrypted, and each block saves, you know, this to for the previous block, and all blocks has to agree. If a certain transaction happens, this transaction doesn't be applied unless all people in the network agrees. So now, if we go use the unified electronic health. But there is the blockchain is an important issue. It can be used for have a unified health record, which is a very good application of it. And finally, I will go fast through what's called the telehealth. As you hear, there's a hospital called the Ahalina. The doctors, you know, help people remotely. Yeah? So this is also spread everywhere in the world. And also we have three-dimensional printing. And as you hear, Dr. Hamoud in Faculty of Engineering Helwan used the manufacturer using 3D printer a reusable mask. Besides also the other ideas. And finally, very important technology is the robots and drones that used to deliver food and minimize, you know, human-to-human interaction, and, you know, deal with waste, hazardous waste. But its main issue is that dehumanization. There is no human deals with the human. So, and there is what's called synthetic biology. It's a lab-based biology to, it could be dual use or misuse, because it's used to develop vaccine in a very fast way using computer science approaches, AI approaches. And there is nanotechnology I'm not going to talk about it because my colleagues will talk about in the coming sessions. Summary, there's 2 points to end off. Many of the state-of-the-art technologies aided for prevention and control of COVID-19. We used it. They are still far off due to 2 issues. Some technical issues and some socio-ethical issues related to legality, privacy, and security. And the governments and the people, societies has to talk about legality and privacy and security issues, because it's a very limiting factor, beside also some technical issues that's not been resolved till this moment.
Yes, of course. Thank you. Thank you, Dr. Mohamed, for this rich presentation. And let me ask you a question. Firstly, what are the limitations of AI, especially in applying in such a domain such as COVID-19?
Yeah.
And how to overcome them, these limitations?
Yes, yes. Very good question. And actually, it's an important question, because this what's caused, limited, AI of using it, especially in prediction and treatment, is the lack of information. Lack of information and lack of data is a very important issue affecting the AI. And if we could have more information fed to the AI or the machine learning engine, it could, have a better results and more accurate prediction results. Also, if we could have some information about the virus, about virus mutation and the details from the medical scientists, this will help also AI engine to work effectively and help much.
Thank you. The other question comes in the chat. You talked about blockchain. Is there a preferred usage for blockchain in this case in COVID-19?
Yes, actually, I didn't have a chance to cover all of it because of the time limitation. But maybe we go to here. There are some applications here, like donation tracking, something related to donation tracking, because the donor doesn't want his money to go anywhere. He want to make sure that he is a trusted, source. It goes to the correct person. Huh? So this used, for authentication, that the donation went to the correct person. Also, managed health insurance claim can be done. So we go to paperless. Also, we track infections, death, and recoveries in real time worldwide. And it traces demands and supply chains of medical supplies. These are 4 applications very famous now, and it is used efficiently and successfully in many places.
Thank you. Dr. Mahmoud will complete the questions.
Yes, Dr. Aida. Thank you, Dr. Mohamed, for your interesting presentation. And actually, it have amount of valuable information you delivered to all of us in your presentation. I have a couple of questions, one from me and the other from the chat group. The first one, I would like to know from your point of view and based on your experience, what do you think which of the technologies you mentioned in your presentation might be applied in Egypt in the coming days or in the coming months?
There are some, many researchers have done a good job in AI many years ago, but we can continue on this, build on that. But it needs, somebody, in the center, to collect such efforts and build on it. Internet of Things also can be done, no problem. If we can go to this issue, it can be done also. Telehealth, of course, we already saw it in the Ahalina hospital or whatever. We can also, develop this more to have it, more effectively. 3D printer also is doing a good job, because we already seen a product, that's 3D printed, using 3D printers. Other things, robots and drones, it has some legal issues, especially drones. It has to be under the authority, supervision. Some security issues related to the national security. Robots also can be used, but unfortunately, due to the infrastructure in Egypt, can be used in a certain places, But it can be used in hospitals mainly, because in hospitals can be used in hospitals to minimize human-to-human interaction. So of course I couldn't go through robots fast because of the time limitation, but the presentation is there. It has some details about the usage of robots.
Yeah. Thank you. Just the second, my quick question is about what is your suggestion to start or enforcing the adoption of such technologies in the research community and industry, especially in Egypt?
Yes. Of course, we can start by our beloved university, Helwan University, and by fostering, and what you call gives incentives of multidisciplinary research. So many specialization work together, to apply, this diversity will help, to make some of these technologies effective and to have a good outcome. So that the multidiscipline is very important. Multidisciplinary research, very important. Secondly, we have to find an industrial partner that might be interested, to apply such technology to have a real product. This will help to fund such technologies and to have something, tangible in the market that can be used by governments and people.
Okay, thank you very much. Dr. Ahmed, do you have any question regarding to this talk?
Thank you very much for the kind talk, and we can move. Thank you, Dr. El-Dakroury.
Thank you, Dr. Ahmed. Thank you, Dr. Ruwaida and Dr. Mahmoud. Thank you so much.
Thank you very much, Dr. Mohamed. And now I leave the floor to Dr. Ahmed, which he will leading the coming 3 talks, which are mainly focused on nanotechnology, and Dr. Ahmed is a specialist in this domain. Okay, go ahead. The floor with you, Dr. Ahmed.
Okay, thank you, Dr. Mahmoud. Thank you, dear colleagues and professors. Actually, now we will move to another technology, a modern technology actually of these tiny molecules that carries a big hope for COVID-19 patients. So let's welcome our next speaker, Dr. Yasmin Abo-zeid, Assistant Professor of Pharmaceutics. Dr. Yasmin got her PhD from University of Nottingham at UK. Then she moved to Egypt again at Helwan University as assistant professor. Then she worked as international and financial cooperation projects expert and was the nanotechnology project coordinator in strategic planning unit at Helwan University. She attended many international conferences and many workshops and talks, and she got a postdoctoral fellowship from a Newton Musharrafa Fund and another fellowship from Islamic Development Bank. And I hope we will enjoy Dr. Yasmin talk. So Dr. Yasmin, you are welcome, and the floor is yours.
Thanks a lot, Dr. If my screens are shared now. Thanks for the conference organization headed by Professor Dr. Mona and Dr. Ruwaida and all the team working on organization this conference. So my talk today will be about nanotechnology application to combat virus infection, and I'm not gonna be restricted only for SARS-CoV-2. So I'm gonna share with you the recent remarkable results I got through applying nanotechnology to combat virus infection. So first, let me explain what does it mean by nanomedicine. So it's like a branch of medicine where we apply the nanotechnology technique either for therapeutic purpose or for diagnostic application. It could be applied in different diseases, but here we are concerned with its application for antiviral therapy and for diagnostic also of infectious disease, as well as prevention and control spread of infection. So what actually is the benefit of nanotechnology that we might be added for antiviral therapy? Or actually why researchers think about applying nanotechnology for antiviral therapy? So first, we have several drawbacks of antiviral agents, and it's assumed that nanotechnology could overcome these drawbacks. So let's first talk with you about the current antiviral agents are inactive. So far we still actually combating or fighting to find a standard therapy for COVID-19. And although we are trying different antiviral agents, but we still don't have a standard therapy. And this is actually due to a high rate of virus mutation, not only for SARS-CoV-2, but for all the viruses worldwide. So here, this actually graph or chart show you the life cycle of the virus. So if any virus actually to start its infection, it should be first enter into the cells through the receptor-mediated, then it starts through uncoating, and finally its genomic material starts integrating the nucleus and start to do RNA replication and protein synthesis. During RNA replication and protein synthesis, actually the virus recruit a lot of enzymes, either from the host cell or from the virus itself, just to help it to produce more and more virus particles, which actually come out from the cells, from the host cell again, to infect other viruses. As you can see here from this graph, that there are many antiviral agents which can actually track each step in the virus life cycle. But as you can see as well, that most of these antiviral agents, the virus actually managed to develop resistance to this to the virus. Actually, the virus starts to develop resistance to these antiviral agents. Okay, how actually nanotechnology could improve this? So if you check here for protease inhibitors, which are the most commonly used antiviral agents to combat virus infection, so we can see that the virus can resist their actually activity through the efflux system. So if we manage to encapsulate or incorporate this antiviral agent into a nanoparticle and just use it for treatment, it could overcome the efflux system. So it could somehow overcome the resistance due to efflux system. And another advantage actually imparted by the use of nanotechnology is that it could overcome the drawbacks of certain antiviral agents. So here, this slide shows you different antiviral agents with different side effects. So I'm gonna be focused on ribavirin itself. So ribavirin is a broad spectrum antiviral agent, and it shows activity against RNA and DNA viruses. And actually, it was used. It was actually a part of the standard therapy for hepatitis C infection before, and also it was the first line of antiviral agents which used in many other virus infections. So it was used actually for influenza virus infection and also produced in coronavirus infection and many other virus infections such as Ebola. So the problem with this antiviral agent is, as I said, is hemolytic anemia. Okay, let's see in the next slide how nanoparticles could improve this or overcome these drawbacks. So in order to understand the role of nanoparticles, so we need to understand first how ribavirin can cause hemolytic anemia. So ribavirin, when it's given in its conventional therapy, like tablet or capsules, it goes into the bloodstream, and once it's in the bloodstream, it starts to be taken up by nucleoside transporter into red blood cells. So actually, this nucleoside transporter is located in all the surfaces or membrane of cells in the human body. But the problem is especially with red blood cells, and I'm gonna say why this is problematic. Because once it's inside the red blood cells, it actually consumes the ATP from the cells in order to form its mono and triphosphates. Because actually this phosphated derivative of ribavirin are the active antiviral agents. So ribavirin itself is not an antiviral, but its metabolite products after phosphorylation is the active antiviral agents. So when it's consumed ATP, it results in reduction of glutathione, which actually is responsible for keeping the integrity of red blood cells. So when reduced glutathione decreased, it starts to convert the normal cells into hemolyzed erythrocytes. Actually, we done work and we published it before about how we can investigate the efficiency of polymer nanoparticles in overcome these drawbacks. So first, we assume that polymer nanoparticles could overcome the hemolytic anemia caused by ribavirin, and this is mainly because nanoparticles can be taken up into the cells through endostatic pathway, and actually the other red blood cells doesn't have an endostatic mechanism. So in order to investigate our hypothesis, we prepared a fluorescent array of nanoparticles, and we start to compare the mean fluorescence retained, as you can see from this graph, from control red blood cells, which is cells with no treatment of nanoparticles, and then we bring another cells and treat it with nanoparticles for 0 time, and then we watch the cells and track its fluorescence, and then we treated another 2 samples of red blood cells with nanoparticles at different temperature, 4 and 37 degrees, and incubated the nanoparticle with these cells for 1 hour. Then we did a wash step, and we compared the mean fluorescence intensity recovered for all samples. As you can see, there is no actually significant differences between the fluorescence gained. That means that the nanoparticle have like a minimum or no uptake with red blood cells, which means that if we manage to incorporate carbivine into polymer nanoparticles, it could be a promising technique to combat or to overcome the effects of carbivine, and this will be very helpful because carbivine is a really very potent antiviral agent. So other researchers actually start in the literatures, they can incorporate the antiviral agent into nanoparticle, either to improve the pharmacokinetics parameter or improve viability or even increase drug stability or control drug release. In some cases, they incorporate it for selective delivery into certain organs. So let's say for hepatitis C, where it could target actually the liver. As well as it could also overcome the problem of blood-brain barrier, so it can cross the blood-brain barrier, and this will be like a promising strategy for treatment of HIV infections, where actually we can find dominant viruses in the brain, and this is responsible for reinfection or recurrence of the infection in treated patients. So, although all these research works that were performed by researchers, actually the scientists ignore very important questions, because they didn't actually investigate how the nanoparticles could affect the virus, how the nanoparticle uptake or how the virus infection could affect the nanoparticle uptake. And actually this is very important because simply nanoparticles are taken into the cells by endocytic pathway, as I said before, and if the virus infection does some sort of down regulation of the endocytic uptake, that means it will reduce or decrease the uptake of the nanoparticles, and therefore actually the incorporation of antiviral agent or the massive work done to incorporate the antiviral agent into nanoparticles will be a sort of nonsense. So it will not actually improve the antiviral therapy. So actually we asked these questions and started to do some research work over the last few years. And to do this, actually we created 5 models of virus infected cells. We used a hepatitis C virus and another 2 respiratory viruses, which are rhinovirus E16 and rhinovirus 1A. So let's start first with the results I got from hepatitis C virus infection. So first, we infected the U75 cells, which is a liver cell with the virus, and we confirmed the replication of the virus, as you can see here from the green fluorescence and infected in the photo for infected U75 cells. So it actually shows the label virus protein, and the blue one represents the nucleus of the cells. So here, if we compare the infected one versus non-infected, we can see the green process here, which demonstrates the virus infectivity and the virus replication as well. Then we started to treat these non-infected and infected cells with the fluorescent labeled nanoparticles. And as you can see, the red fluorescence here in these images by confocal microscopy denotes actually or reflects the nanoparticle uptake. So from the first time, we can see that we can expect that actually the infected cells take up much more nanoparticles compared to non-infected cells. But when we go for this actually needs to be further confirmed by quantitative study. So we did another quantitative study using flow cytometry, where we tracked the mean fluorescence intensity against different time intervals of nanoparticles in incubation with U75 cells, either infected or non-infected. As you can see here, the orange line represents the mean fluorescence intensity recovered or detected or recorded for infected cells, and actually is much higher than non-infected cells by 2 times more, which actually was like a good breakthrough for us, because it means that the virus infection was the driving force to enhance nanoparticle uptake. And this is very promising. We managed actually to publish this work, and this work was done in collaboration with the University of Nottingham at UK. Then we started to ask another question, and we started to search for it. Is this like a general phenomenon? So all virus infected cells can enhance the nanoparticle uptake. So we started to do to work with rhinoviruses. First, as we did before, we infected the cells and confirmed the virus replication inside the cells using a PCR technique. And then we start to investigate the mean fluorescence intensity again from nanoparticles uptake from nanoviruses infected cells, either, and we use two types of nanoviruses, as I said before. And as you can see here from these graphs, that actually, yeah, we can find some enhancement of nanoparticle uptake, but it's not as dramatic as we found with hepatitis C model. And actually, we first attributed this to the problem might be related to the HeLa cells, because HeLa cells is cervical cells, so it might not be like a good model for nanovirus replication. That's why we moved to try with the B2B cells. Again, we get a similar result. So there is like an enhancement of nanoparticle uptake with virus-infected model, as you can see here with the gray column over the white column here. But still, there is not a dramatic increase of nanoparticle uptake as we found in hepatitis C model. So we started to conclude that we still have a lot of challenges for nanoparticle to improve the antiviral therapy or even to go for clinical translocation.
Dr. Yasmin, kindly.
Investigation for virus infectivity effect on nanoparticle uptake. Also, we need to highlight or understand the potential toxicities that might be imparted by these nanoparticles on the biological system, as well as if it crosses several biological barriers. And also, we need to optimize the condition for larger scale manufacture of nanoparticles. And actually, to go through this, it might need a lot of time. And due to the emergence of coronavirus, so we think about moving or shifting our track to use nanoparticles for control and prevention of infection. So just let me start with giving a brief hint about coronavirus.
Yasmin,
so, what is the history of coronavirus?
Excuse me, Dr. Yasmin.
Coronaviruses are known since 1960, and they were like a common viruses that doesn't impart any severe toxicity in humans. So it could only infect the patient with mild symptoms, which is similar to the flu. But by time of 2002, where SARS-CoV start to appear in Asia, it started to actually infect people worldwide in 29 countries, and it results in around 8,000 cases of infected people with more than 750 deaths. And a few years later, MERS-CoV started to originate as well, which actually is another modification or mutation of the coronaviruses. And also it do the same problem. So it actually spread all over 27 countries and affects around 2,500 people with around 850 deaths, which is actually a higher percentage of deaths recorded here with MERS-CoV more than SARS-CoV. And now we are fighting or facing the problem of COVID-19. So it spread, it becomes more and more mutated virus and more contagious virus, which actually it affects all countries. And now we, according to my check today for the number of people infected, they are around 6.5 million worldwide and around 388,552 deaths, which is really a big number compared to the previous coronavirus model, but it's not. But the percentage of deaths is still very low compared to other viruses relative to the number of people infected. And actually, we still don't know what will happen in the future. So we are facing the possibility of new mutation of the coronaviruses might be very in the next few years. We can find like more contagious virus or more pathogenic viruses from viruses or even from other viruses. So that's why in addition,
hello, Dr. Yasmin.
Problem with the coronavirus is that it spread among people very rapidly, either for the droplets, coarse droplets, or even for airborne transmission. In addition, that it stays on the solid surfaces actually for a long time, which actually ranged from several hours to several days. Furthermore, when we checked for the literatures, we find that the people who actually are very critically ill due to COVID-19, they need to use a ventilator to overcome the problem of respiratory problems. And we find that around 50% of those infected people or patients are died actually due to the hospital-acquired infections, which means that we really need to find a solution to combat this infection and stop its spread, especially that the viruses, as I said before, can stay for several hours and days on solid surfaces. We don't have protective immunity in all population. Also, we don't have a standard therapy antiviral therapy for these viruses. In addition, that we still looking for vaccines. And just to keep in mind that since 1960, where the coronaviruses are known, until now we didn't actually succeed to develop any vaccines. Hopefully, the people, the researchers, actually can provide us with a proper vaccine in the coming few years. But we need to make like a rapid action to combat these infections. That's why we think about using nanotechnology to produce or manufacture self-sanitizer products. So by its own, these products can kill the viruses and bacteria, and therefore it could limit the spread of infection. So we started to survey the literature
Dr.
and
Yasmin.
all
Hello, Dr. Yasmin.
Nanoparticles, and we found that these metal oxide nanoparticles have many characteristics. So they have a broad antimicrobial activity, which means that they are active against viruses, bacteria, fungi, and parasites. Also, the microorganisms are not able to develop any resistance to these metal oxide nanoparticles, which is a very promising technique. And this is actually mainly due to the mechanism of action, which depends on the production of the active oxygen species. And this results in the oxidation of different biological sites in the microorganism, and this ended by the microorganism death. So just to make the things is just easier
Dr. Yasmin.
to understand, it's assumed that this is the virus particle for SARS-CoV-2. It needs actually here this lytic thing on the surface represents the spike proteins, which actually required for the virus to interact with the receptor, AC2 receptors, and then it should enter into the cell and start
Dr. Yasmin.
activity. So our hypothesis is saying that if these metal oxide nanoparticles come in contact with the surface of the virus particle, it would start to oxidize these spike proteins and also
Dr. Yasmin, please, the voice.
And this can them inactive, so the virus can't actually bind with the human cell receptors and do its infectivity, which could be considered as a good strategy to combat or control the virus infection. Actually, we selected a certain model, and we do of metal oxide nanoparticles, and we did a document study to emphasize our hypothesis if these metal oxide nanoparticles could actually interfere with spike protein and lipid envelope of SARS-CoV-2, and we find that we get a promising results. And actually, it could interact and
Dr. Yasmin,
leading to some.
We cannot hear you.
Virus as well. And this work actually has been accepted for publication in European Journal of Pharmaceutical Science. Then we started to write, we actually managed to work 2 projects and they are submitted for STIFA for funding. And this project actually is in cooperation with the University of Nottingham, where we think about developing a nano or self-nano sanitizer textile product or fabric product to combat or control the COVID-19 infection among his providers. So simply to explain my idea is that we will have here certain textile which actually is modified by these yellow circles which represent the metal oxide nanoparticles. So we assume that when infected patients start to sneeze or cough, and this actually droplets carried into these modified fabrics, the metal oxide nanoparticles start to release active oxygen species, and this will damage the SARS-CoV. Then we also go for another model for another project where we can use the same technology of metal oxide nanoparticles to obtain or to cover the solid surfaces, and this actually would protect also the viruses from any further infectivity among people. So this actually project is in cooperation with German University and also with University of Birmingham. And finally, I'm going to conclude my remarks or my work that we still need future work in order to recruit or use nanoparticles for clinical translation and improve antiviral therapy. But metal oxide nanoparticles could be considered as a promising strategy to produce or manufacture self-sanitizer product. Finally, I'd like to thank all my cooperators and funding agency or sponsors. And now I'd like to thank you for your listening, and I will be happy to give any more questions.
Hey, thank you, Dr. Yasmin, for a very interesting presentation. Actually, we was trying to reach you to just raise your voice, but I hope it was very illustrative. Okay, now I have one question to you, and could be one another from the chat. Do you hear me? Did you hear me, Dr. Yasmin?
Yeah. I can hear you clearly.
Oh, okay, great. As you said, the nanoparticles could interfere with the cells via cell-mediated endocytosis, and it interferes with different biological pathways. And there is a raised issue about the safety of nanoparticles. From your point of view, how we can manage this issue of safety of nanoparticles if it was out of our control? Thank you.
Okay, so the safety of nanoparticles, it depends on the material of nanoparticle you use. So let's assume if we use a polymer nanoparticles, which actually I'm using for therapy. These polymers should be a biodegradable polymers, so they wouldn't impact any toxicity. The problem actually might come from the metal oxide nanoparticles if you use it for treatment, because metal oxide nanoparticles can be degraded by the biological system. And this is still a problem, but recent researchers actually saying that making or using a green synthesis methodology to synthesize the nanoparticles will be adding a less harmful for these metal oxide nanoparticles. And actually, we managed to synthesize these nanoparticles in our lab at the School of Pharmacy using a green synthesis. And we currently investigating its cytotoxic activity against some certain cell lines.
Okay, thank you. The next question from chat, actually it is about the utilization of nanoparticles now in your studies was in cell lines, in vitro cell lines. Do you have any experience or from recent research for other in vivo studies, or it started on human or not?
Okay.
Drug delivery, I mean.
Okay. Human, you can find that many liposomal delivery system will actually accepted and now approved by FDA for treatment of cancer therapy, but still we don't have any available nano delivery system accepted for fighting of virus infections. So yeah, the technology is applicable and it could be translated for human, but it needs actually a lot of time to go for the translation. As I said before, that we need to make sure that of the safety of these nanoparticles. Also, we need to figure out if it could cross certain biological system or could target certain organs in the human body as well.
Okay, thank you, Dr. Yasmin, for a very interesting talk and for your kind contribution. Thank you. Now we are moving to another direction in our session. For a prevention strategy via maintaining a good hygiene and creating new disinfectant and sanitizers. Our next speaker, Dr. Ahmed Hassan, a lecturer of microbiology at Faculty of Science, Helwan University. And he got his master's degree via Erasmus Mundus program from Bulgaria and his PhD in microbiology. And now he will talk to us about creating a new disinfectant utilizing silver nanoparticles. Welcome, Dr. Ahmed, and the floor is yours. Kindly start.
Okay. Good evening, everyone. Let me introduce myself. I am Ahmed Hassan Ibrahim, Assistant Professor at Botany and Microbiology Department. Also, I am work as Senior at Bioinformatics Center at Faculty of Science. We have a good effort in using nanoparticle as an antiviral.
Dr. Ahmed, could you start to share your slide?
Okay. I think Dr. Yasmin must. Yeah.
We saw your video now. You are fully full screen.
Okay.
Hi.
Our project about manufacture of hand sanitizer based on silver nanoparticle. My team of work, me and Dr. Salim Abdelaziz and the PhD student Ya Osman. I will speak briefly about nanotechnology and silver nanoparticle. Nanotechnology is having a profound impact on the development of new class of hand sanitizer. Silver nanoparticle size less than 100 nanometer have a superior antibacterial, antiviral, antifungal properties. In recent years, silver nanoparticles have received a great deal of attention from many research working on multidiscipline due to their unique feature and wide spectrum application in food science and medical and agriculture. Silver nanoparticles show antimicrobial activity against E. coli, Staphylococcus aureus, Serratia marcescens, and also antiviral activity and anti-cancer activity and anti-inflammatory effect. There are different methods that used for synthesis of silver nanoparticle: chemical and biological and physical methods. Chemical method including chemical reduction, microemulsion, radiation, hybrid method, photochemical reduction, and sonic electrochemical microwave-based system. And recently, green synthesis route or biological method, the most effective regarding its eco-friendly and cost effective. This is the method that used for nanoparticle synthesis, metal nanoparticle and silver nanoparticle. We have here chemical and physical method and biological method. Biological method, we can use bacteria, fungi, plant, yeast, algae. There is a growing need to use economic, eco-friendly, and green synthesis routes that use non-toxic chemical in the synthesis protocol of nanosilver. Green synthesis of silver nanoparticle synthesis using microorganisms, plant, and algae. Most recently, World Health Organization on its electronic site at silver nanoparticle as Sanitizer against coronavirus or COVID-19. We try to use plant material. The plant material can be more beneficial for nanosilver synthesis than bacterial and chemical method because of no threat of bacterial infection, dangerous chemical contamination. Moreover, the green synthesis of silver based on plant extract mechanism elevate the metal ion due to the presence of functional molecules such as phenol, terpenoid, ketone, carboxylic acid, enzyme, amide. Recent research reported that silver has been synthesized using a variety of natural plant, leaf extract of citrus, lemon, green tea, coffee arabic, gum arabic, aloe vera plant extract, root extract of morinda. The method, we use plant extract from leaf and then we add silver salt. Then we make the reduction for silver nanoparticle using some constituent from the plant extract. Then we produce silver nanoparticles that used as antifungal, anti-cancer, antiviral, or antibacterial. We have different types of silver nanoparticle have antiviral activity. This silver nanoparticle may be naked or may be coated with PVB, polysaccharide, or any other ligand. From the coated nanoparticle, we use it against herb simplex virus, HIV, and other virus. And the naked virus can be used with hepatitis virus B and influenza virus. We used in our study camphor plant extract. Camphor, a fumigant during the Black Death in the 14th century, and cultivated fragrant wood in ancient Egypt and Babylon. The fragrant camphor tree and its products such as camphor oil have been cultivated since ancient time, have a rich history of traditional use. It was used as fumigant during the era of the Black Death that caused by bacteria, Yersinia pestis. Here we have a camphor tree. Camphor tree cover all Arab Republic of Egypt, and we have here in our university about 50 camphor tree. Camphor Why we use camphor? Camphor exhibits several biological properties such as antimicrobial, antibacterial, antiviral, antifungal, and anti-cancer effect. Camphor is a common ingredient in more medicine, in topical applied, analgesic, and ruby efficient for treatment of many muscle aches and pains. However, camphor is poisonous when ingested and can cause seizure, confusion, irritability, and neuromuscle hyperactivity. The lethal dose in human is reported to be 50 and 500 milligram per kilogram body weight.
Dr. Ahmed,
Based on the using of camphor leaf extract, which is very effective in silver nanoparticle synthesis. Camphor tree leaf are available all over the Arab Republic of Egypt, and this will result in low production cost. By this method, the cost of 1 liter silver nanoparticle with average size of 10 nanometer and concentration of 10 ppm is about 5 Egyptian pound, which is very effective as hand synthesizer and very cheap than ethanol. Chemical constituent of crude extract of camphor: acetic, formic, isobutyric, propionic, isovaleric, and camphor oil. This is the chemical structure of camphor that used as antiviral agent. Here we have chemical and physical properties of camphor: the water solubility, the pH, the physiological change, hydrogen acceptor and hydrogen donor. Symbiotic use of camphor: anti-infective agent. It used for as antiviral against influenza and against herpes simplex virus. It was used in human for inflamed joints, pain, and rheumatic and other inflammatory conditions such as cold in throat and chest. Camphor exhibits the high efficiency as an agent inhibiting the production of influenza virus, including dimeric camphor derivative. Camphor also has the ability to deactivate herpes simplex virus. Camphor and COVID-19. Camphor and COVID-19 target protein prediction. We have 5 target protein: endoRNase protein, helicase protein, RNA polymerase protease, and spike glycoprotein for COVID-19. And we estimate and predict the activity of camphor against this 5 protein. We found that it has a good inhibitory activity against protease and helicase protein for COVID-19. The method for silver nanoparticle synthesis, it's a simple method. We collect camphor leaf, preparation of, then we prepare silver solution, silver nitrate solution, and we add silver nitrate with plant extract. Then we make steering for both silver nitrate and the plant extract. And after about 1 hour, we get silver nanoparticle that coated with camphor. And the size of camphor here, the average size of camphor, we get about 80 nanometer, and we try to make it about 10 nanometer, as we can reduce the size of nanoparticle. As we can reduce the size, the activity of the nanoparticle can be against antiviral, antibacterial, and antifungal activity. Our product will be nanosilver solution spray and the nanosilver gel.
The size of
solution spray of camphor disinfect and sensitize against harmful bacteria and virus, prevent virus microbial causing skin-related problem and anti-odor. It can also be used to pre-treat NABI and diaper to prevent NABI rash. Reference. Thank you.
Great. Thank you, Dr. Ahmed. Very nice talk, and very direct, and I hope to succeed. Now you are in the middle of your research of this project.
Yes.
Okay, so we will just have one question to you. You know, Dr. Mustafa Said called or gives the name of nanotechnology as a technology for poor people. From your point of view, this a cost for this product, the spray and gel. It will be, it will be affordable for lay people, for the normal people, for the poor patients, or it will be costly because you are using silver as the input of this manufacturing process.
Okay.
I'm talking about the cost, you know, the cost. It will be costly, or from your point of view, it will be not cost.
It will be not cost because 100 gram of silver nitrate will produce or will synthesize about 100 ton of synthesizer. So if we collect or we estimate the price for silver nitrate solution, it's about 4,000 pounds. So we can speak about 100 ton of nano silver will cost about 10,000.
Great, 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 great. A big hope for this still tiny molecules, Dr. Ahmed, for as a disinfectant and sanitizers. Thank you very much for your kind contribution and very nice presentation. And of course, there is a lot of efforts at Helwan University and Faculty of Science and Faculty of Pharmacy for utilizing nanoparticles. And Dr. Ahmed, one of those. And to me, I'm happy to work with Dr. Ahmed with a funded project from ASRT. Good luck, Dr. Ahmed, and thank you. Now we will move for our last speaker, and Professor Yasser Shabana, Professor and the Chair of Mechanical Design Department, Faculty of Engineering-Mataria, Helwan University in Egypt. It will be our last presentation and a new direction for testing. A lot of talks in last months is about availability of testing for COVID-19 and how to make it possible and how to make large screening process. One of these solutions is to develop a new biosensors. Dr. Yasser will speak about modeling, analysis, and fabrication of Nano-Bio-Sensor for detecting COVID-19 and other diseases, a collaborative work with his student with a funded project from STDF. You're welcome, Dr. Yasser, and I should have a limited time, so I hope to stick with the time, and the floor is yours, and you're welcome.
Thank you very much, Chairman. My title today is Modeling, Analysis, and Fabrication of Nano-Bio-Sensors for Detecting COVID-19 and Other Diseases. This work is part of a graduation project with bachelor students at the Faculty of Engineering at Mataria. We know fabrication is very costly, especially when we deal with nano size that lead to atomic size. And therefore, we started with modeling first in order to have some equations or model to predict the behavior of sensors, and then analyze this model and verify its results in order to fabricate it. So the first step is to model, then analyze, and be sure that the results are acceptable. Then we choose the optimum parameters, optimum values of different parameters to fabricate a nano-biosensor. You know, related to medicine, there are two parts related to medicine, which is first step is to diagnose. And the second is to have a proper medicine. Diagnostic is related to sensors to some extent. And when we cooperate or manage the nanotechnology in order to have correct diagnosis of different diseases, then we have this advanced technology. And we are going to combine advanced technologies and advanced materials also in order to have a proper nano sensor for predicting or detecting different diseases. The point is, if you have an analyte, or in other words, like disease or any atoms, we have to have sensor. And this sensor attract or has chemical reaction with the analyte. And then the signal is converted to the transducer. And after the signal, the output signal of the transducer should be post-processed for measurement purposes. So in our biosensor, we are using cantilever beam, but micro size and nano size. Since the thickness of this cantilever is around 0.3 micron, and the length is about 180 micron. And when the analyte is absorbed on the sensor here, then there is intermolecular reaction that causes surface stress, and therefore force induces. And this force try to bend the beam, either upward or downward. So finally, the behavior of the sensor is related to the deflection. The beam is going to be deflected upward or downward. And the amount of deflection, or the value of this deflection, is depending mainly on the virus. Therefore, we can calibrate our sensor to detect a wide range of viruses by calibrating the value of this deflection according to different viruses. So for advanced materials nowadays, we have what is called functionally graded materials, or functionally graded concept. That means any parameter is varying with the dimension. For example, here in our sensor, the red color represents the modulus of elasticity, or Young's modulus, for example. So the modulus of elasticity, or Young's modulus, has certain value on the tip or the free end. And this modulus, or elastic modulus, is varying continuously with the length, and has different value at the fixed end on the other side. So this is the concept of functionally graded. And in our study, we are going to vary the modulus of elasticity, which is the main property of any material controlling the behavior, and also the thickness of the biosensor. As you see, the thickness is varying continuously with the length. This gives actually good results related to accuracy, because accuracy is depending mainly on the behavior, and the behavior is controlled by the deflection. And by varying these two main parameters, we can control the deflection, and therefore control the accuracy. So these here, the aim and the objectives, and the main aim of our biosensor is to have high sensitivity and accuracy, of course. Other points here are for the objectives. Modeling of the biosensor, we are modifying model based on energy analysis proposed by Jean in 2008, and we took this model based on the energy and modified it to be valid for our functionally graded concept. Because if we take it as it is not valid, because our parameters are varying with the length. Since we have here like adsorbed atoms and substrate or materials atoms, there are some energies act on the system. And the energy can be divided into three parts. The first part is the intermolecular energy between the adsorbents and the energy between the atoms, or the substrate or the material atom, and the energy between the absorbent and the atoms. And this relation is predicting the energy between any two atoms, where A alpha and B alpha are constants. When alpha equals 1, this is related to the interaction between the atom, and if alpha equals 2, this stands for the interaction between atom and substrate. R is the distance between the two atoms. If we have our cantilever here in original conditions or initial condition, it should be straight like the top figure here. But if we have intermolecular reaction or interaction, the surface stress and force induce, and therefore the beam is bent like this, or even upward or downward. And therefore the distances between the atoms and also between the atom are changing according to the adsorption density and some other parameters. To skip this actually modeling, because it is very long and very mathematical computations here, the total interaction
just 5 minutes, Dr. Yasser.
Sorry?
Just 5 minutes, please.
Okay.
Thank you.
The interaction energy here can be represented by the integration of the sub-energies, which is between the atom and between the atom and the atoms at the surface. Then we add the elastic strain energy. The elastic strain energy depends mainly on the modulus of elasticity and the moment of inertia. Moment of inertia of the cross-section represents resistance to rotation. That means if we increase the thickness, for example, the moment of inertia or the resistance to rotation is increased. The total energy equals here the substrate energy and the surface energy, and then we can add it to the intermolecular energy between the atom. And finally, we are going to apply minimization approach in order to minimize this total energy, and then we can get the deflection at any point on the sensor. Mainly, the tip is a free end, and it has the maximum deflection. And the maximum deflection is very important for detecting different diseases. Since we are going to vary different parameters, like for example, parameter Px, P stands for Young's modulus or modulus of elasticity, and also the thickness of the biosensor. And we use here power function, power law, that controls the variation. And n is the exponent. When the exponent is less than 1, like 0.1, the property or the parameter is sharply changing at the fixed end of the beam or the sensor to the free end, to the value at the free end. But if n equals 1, the variation is linear, as we see here. If n greater than 1, then the variation is like very small at the beginning, and then sharply change at the free end. Therefore, this thickness variation, the top surface is following these curves according to the value of the exponent. For the results, we define some parameters like RE. RE stands for the ratio of Young's modulus at the free end to that at the fixed end. So if we have, for example, RE equals 0.25, that means if Young's modulus at the fixed end is 100, then its value at the free end is 25. So this means it is soft. Therefore, we predict high value of the deflection at the free end. This, the horizontal axis represents the relative adsorption density, and the vertical axis represents the deflection at the free end. We can see that the deflection has different values at different RE, or Young's modulus ratio. Therefore, we can extract or choose the proper value of this ratio to design our sensor to meet certain requirements. Also here, the effect of the exponent of the gradation function. If the gradation exponent is 0.1, for example, we mentioned that the property or the parameter is sharply changing at the fixed end. Therefore, we expect n equals 0.1 has less resistance, and therefore the deflection is very high for lower values of the exponent.
Okay.
When the exponent increases, the deflection decreases. This is another parameter.
Just 2 minutes, please.
This is another parameter to choose for designing proper sensor. Then H represents here the thickness of the biosensor. And we mentioned that our thickness is going to vary with the length or in the longitudinal direction. And if RH equals 0.1, that means the thickness at the free end is 10% of that at the fixed end. And therefore, we can predict here, as you see, the deflection at the free end for various values of the thickness ratio. And here is also the exponent of the thickness according to the gradation function. And we can see that for lower values of the exponent, the deflection is very high. The conclusion is we can choose the proper values or have optimum design of the biosensor before fabrication. Then we can choose RH, NH, RE, and NE. Here also the effect of combination between RE, RH, and NE, NH, so that we can have like a wide range of values to have some insight about what if we combine the changing of both at the same time. And this helps for optimum design of the biosensor. Also here, the effect of the length of the biosensor itself when using linear variation of the parameters. So the main point is to properly design and select different values of different parameters before fabrication. For the design purpose, we need to know the force induced on the sensor for design purposes. So here, this figure represents the force with the NE exponent of Young's modulus. And we can see that the force increases at the beginning up to exponent equals 1 and then decreases monotonically as you see here. And this is the effect of RH and NH. H is related to the thickness, and we can choose also the best values that give a safe design.
Thank you very much.
For the conclusion, as you see, functionally graded micro and nano biosensors are manufactured based, are modeled based on the energy principles, and we can conclude this in one sentence. We can fabricate a biosensor with high sensitivity according to the different parameters that we considered. Thank you very much.
Thank you very much, Dr. Yasser. Very interesting and a lot of details. I'm sure that people of engineering and physicists are very happy with this, by this illustrative talk. Maybe the biologists are missing some parts because, you know, this bio-nano sensor. So I will just ask you just a very quick question. How this theoretical model and modeling transferred to a real product? What is the support that you need? Just briefly in 1 minute.
Yeah, the title actually includes fabrication. So we did the first 2 steps, which are the modeling and simulation or analysis. And we verified our results with some other experimental results in the literature for constant thickness and constant Young's modulus. And now we are contacting different like agencies and universities in order to fabricate, because we need some like special instrumentations related to nanotechnology. Okay. And we are contacting actually Egypt, Japan University and Burj Al Arab, and also American University. And we actually expanding our hand to our colleagues who are attending this conference. If we can cooperate together, especially we have some undergraduate students who are making the major part of this work.
Okay, thank you, Dr. Yasser. Of course, there is a lot of colleagues and can cooperate with you, and that Faculty of Science, our colleagues got a funded project from
and we have also, if someone is interested or has some instrumentations, we have some fund actually by ASRT, Academy of Science and Technology. So we have some money actually that we can pay for the.
Thank you very much, Dr. Yasser. Kindly ask that just to close the windows that so I can share just the last photo. Thank you very much. And before I will give the talk to Dr. Ruwaida to close the session, I'd like thank you everybody, and I'd like to highlight that Dr. Yasser kindly just shut down the video, so because we are sharing now.
Okay. I'd
like to share this page, this pic with you. Credit for Dr. Mohamed Al-Qassas and Dr. Mukhtar Bakr for sharing this via social media. I call it the responsible science. A lot of people now are looking for scientists and technologists to develop some solution. Dr. Ruwaida, kindly you can now close the session, and thank you very much, Dr. Mahmoud Al-Misalawi and my colleagues, speakers, and all the organizers. Thank you very much.
Thank you. The REACH session provides insight on the current efforts and the technological research in Helwan University to face the challenges of coronavirus pandemic, like role of AI and nanotechnology in prevention and the diagnosis of COVID-19. We recommend much more work in research tracks of AI, IoT, nanotechnology, and robotics, with making sure for the availability of assisting labs, consider more multidisciplinary, interdisciplinary researches, and integrating with various technologies to help in defense COVID-19 and in post-pandemic. More collaboration with the health sector is required to build a benchmark data set to efficiently use AI, the new emerging technologies, and data science. At the end of this session, I would like to thank our speakers, attendees, organizers, and the moderators for their active participation and the kind contributions. Thank you.
Thank you very much.
Wish you very much for all of you.
Thank you, Dr. Mahmoud. Thank you, Dr. Ruwaida. Thank you. Bye.